Welcome, everybody. Welcome now to our economics day. So you are now at the point where you've completed the fundamentals. Yeah, like we've covered the whole fundamentals of passive house. And you learned that we're having this building envelope, that we are creating a really high thermal envelope, like really good thermal envelope. Then we create this sealed box. But now we can't live in a sealed box, so we need fresh air. That's the reason we're putting in the heat recovery ventilation system. And as it is not 100% inert to the outer environment, we now actually need to condition it and heat and cool it, or dehumidify or humidify it, depending on the situation. So that's the fundamentals that we learned and that we put together so far. Let us look at that in a little bit a different angle from what we've learned. So far, you learned about characteristics of materials. Yeah, you heard about the lambda value. Yeah, so you heard about the lambda value. Lambda, what was lambda? You remember what was lambda? Yeah, the thermal conductivity. Yeah, and that we learned that, for example, aluminium has a lambda value of 160 watts per meter. And we have, for example, fiberglass fiber has a lambda value of 0.04 watts per meter Kelvin. Sorry, the Kelvin is missing. So this is what we learned, that aluminium has a really high conductivity and fiber insulation has a really low thermal conductivity. This is the reason we're using fiber as thermal insulation, and that's the first thermal conductivity. That's the first material characteristic that we learned. Then we learned about thermal capacity. Yeah, the capacity. That was that little CP that we're having. That's the capacity of material. And the only one that we're really looking at is the capacity that we're always talking about in passive house. Is the air. We're looking at air as the capacity with 0.33 watt hours per meter cube Kelvin. Yeah, and if you look now at water, concrete, and steel that we've done really early on, then we see that air has a really, really low capacity. If you're looking now to water has a capacity of 1,162 62 watt hours per meter cube. If you look at concrete, we're having concrete has 555 watt hours per meter cube Kelvin, and steel has 975 watt hours per meter cube Kelvin. Yeah, so now when we're looking at our systems that we're using for conditioning a place, we're normally looking at air or water. We're having a air conditioning system, or we're having a split system, and all what they're using as a medium is normally air, and then we're pumping that air around. The other option that we're having is normally water, that we're using water that we pump around. So that's like a chilling ceiling, a chilling wall, a radiator, an underfloor heating system. They're normally water-based. And now you see already that massive difference of the capacity of these two materials. This is the reason why water creates a really quick overreaction and overcorrection of the temperatures indoors, because we are at more than 3,000 times the capacity for the same volume. And that's the reason we have to be really careful with water-based systems in a passive house. Then the next value that we looked at, or like actually earlier, was the G value. The G value. What was the G value? That's the solar heat gain coefficient at the end, or like similar to the solar heat coefficient, and has no unit, and it's just telling us how much of the heat radiation, of the solar radiation, is coming through our glazing. And we always want to have our G value only related to the glazing. We don't want to use a solar heat gain coefficient that includes the frame. This is completely giving us wrong results. This is the reason we really want to have a G value and making sure it's the value of the glazing and not from the overall window, because otherwise we're coming to the wrong results. And then we had another material characteristic that was our mu. Remember what that was for?
Vapor?
That was the vapor resistance. Yeah, so that was vapor transport. Vapor transport, and here out of this we got our SD value. Yeah, so that was that. Of the G value, we're getting our solar radiation. Of the capacity, we're getting our movement. Here is the QS we're getting out of this, or the PS. This is what comes out. Maybe I do that in different colors. So like the result out of this is the SD value. And the SD value is the layer of air, like a layer of air that is lying on the material on the way. That's the air, the pressure that is on it. I often see it easier to see it with a water column standing on it, and that's the height of the water column until it pushes the vapor through the material. So it's the vapor resistance, and the SD value is representing that in meters. Yeah, maybe good to know. So this comes out of our mu value. Then we're having here the G value gets us the QS or the PS, like the solar radiation gains or the loads that we're having. Then the capacity is giving us the QV. Yeah, so that's once the ventilation and infiltration. So we're having here vent or infiltration. Yeah, from infiltration, the unperfect building envelope, or ventilation, what comes from the heat recovery ventilation system. And then the lambda is our QT calculation. Yeah, that the QT that we're looking at is the transmissions of the material. We have the transmissions for our wall, for our roof, for our ground, for our frame, for our glazing. All of them, they're letting heat through, and that transport we are looking at with the lambda value of the materials. They're coming out of that. And then, so that's related mainly to the U value, but not only U value, and we calculated U values as well. We had our psi, our point thermal bridges, and our linear thermal bridges, and they all are playing into that thermal envelope performance of this building envelope that we're looking at. So the U value, psi value, and psi value. And we're looking at them, how much energy is getting transported. It's always like Kelvin, Kelvin, Kelvin. We're always having in that solar radiation has no Kelvin because it's solar radiation. Like that works a bit different, but here you see it's always looking at the thermal difference and how much energy we're letting through the material, or how much energy is it transporting. So that was the first thing we looked at. How much energy can air transport? Yeah, we went through that already with talking about the water and the air. So that this is the reason why when we're looking at air cannot transport a lot of energy to the volume, because it has not a high capacity. And this is the reason why this is perfect for a passive house, because we can switch on and switch off immediately. So we reach the temperature, we switch it off. Now we're happy. Soon we need correction, then we're just letting the system run again. The water system is different. The water system, we can switch it on, and then it takes a while until it actually comes to the radiator. And then when I switch off the radiator, it takes a while until all that heat of the radiator is actually coming out. This is the reason why our forward flow temperatures in a radiator need to be really, really low, like just a little bit above what we want, so that we're not overcorrecting our temperature in the building. So then we looked at the whole magic formula that I already showed you a little bit at the end. Yeah, we looked at the Q side, the material characteristics like the lambda, the capacity, the G value, the mu value. And then when we looked at that, out of this, we got our energy flows of the different buildups and materials that we have and how that actually happens. Then we came to the magic formula, and we saw that these calculations, they are all related to each other. The only difference between them is the dimension that we're having. So with the psi with the point thermal bridges, it's no dimension, it's just a point without a dimension. So there's no meterage in that calculation. Then we're coming to the linear thermal bridge. The linear thermal bridge has a meter in there, so it's the first dimension, a linear relation. Then we're having meters in there. And then after that, we come to our areas. So second dimension with our U value calculation, and then we're coming to our third dimension, our volume calculation, what is always for us air in our situation. So this is what we learned, that these magic formulas, the only difference is the dimensions between the different things that we calculate, but at the end, everything is the same. And then we learned that the difference between the demand and the load is just that climate part of it. In the demand, we're using the heating degree hours that you just calculated earlier. And in the load, we're looking at the maximum thermal difference. And that's and with this, you understood the magic formula, how that is all coming together at the end. All this, what is it? Probably 20 plus formulas that you need. They're now all the same formula because you know how they are related to each other. And when you're looking at that page, you're now understanding that page and see the relation between these different things. And then we learned, okay, we can improve the thermal envelope, and we can make sure that that thermal envelope really works well and that our heat recovery ventilation system has nearly no losses. But we still have a little bit of losses, and that's now the conditioning part of the building. And the conditioning part is now something that we can optimize as well. And that's something we learned yesterday, that the optimizing our conditioning of our indoor environment and of our domestic hot water is really important, that we're getting that right. And we can always improve the building envelope, or we can improve the conditioning system, or we can even improve the domestic hot water to some extent. It has that all plays together. And you always need to look at the holistic situation of the whole thing. Now there is something that is a little bit annoying. So if you think now you're using a super efficient conditioning system, yeah, you're spending a lot of money on a conditioning system, and you're putting it in a passive house or you're putting it in a conventional house. In which one do you have a quicker return of investment? In the conventional house, because you're needing more energy. And so now the savings of the system is higher in a shorter period of time. And now it's more economical to put like a really efficient system in a conventional house and not in a passive house. So the return of investment is earlier in a conventional house that has more losses, because you're able to recover more energy in a shorter time. However, the whole system is less efficient. And this is where now this professional blindness comes into play. Can the conditioning, can the mechanical engineer find a solution for you that is really efficient on the needs that your building has? Yes, he can optimize that. Yes, you can spend a lot of money on that. But at the end, it's not necessarily the best outcome overall. And this is what Passive House is looking at. So Passive House is optimizing now the building envelope. And now we sometimes even get away with using direct electricity in a bathroom, where we're switching it on for 10 minutes, 15 minutes, like a little fan heater would be okay in that case, because the demand, the amount of energy that we need is so small. So there is now a little bit this like in a Passive House, the conditioning system If it's not so efficient, it's not so important. If it's for short periods, like a bathroom heating or something like that. However, even in a passive house, it really makes sense to optimize the conditioning system as well. So you can always bring that into an economical equation and looking at where is this additional $5,000 spent best. Is it in our windows? Is it in shading devices? Is it in the U value of the roof, in the wall to the ground? Is it my conditioning system? All that things you can look at and say, okay, the best return of investment is now actually when I buy that glazing, for example, that triple glazing that maybe cost me $5,000 more from a double to a triple glazing, but now I'm saving so much energy over the next 10 years that it has the highest return of investment when I compare it with all the other options, like more thermal insulation in the roof, more thermal insulation in the wall, or a better conditioning system or better heat recovery ventilation system. And this is now what the software is doing, or like that you can do with the software, that in the software you're changing things, you look to the economical part, and then you can make your economical decisions. And that's the part that we're actually doing today, that we're actually starting to understand that passive house is an economical optimization tool. We have now the fundamentals. Yeah, we've learned the building physics and building science. And now, because we're sticking to physics and science, now we can actually apply the laws of economics as well. What we can't do with a star rating, we can't do that with a living building challenge. We can't do that with a green star rating. All that stuff can't do this, but passive house can do that. Passive house can now optimize your building economically by actual figures, because we're sticking to the laws of thermodynamics and energy transports. Yeah, so this is now the part that you're learning today. Yeah, another thing you learned yesterday is like, think about the building that you're building should be used for a half a century, or more than a century. So when we're designing something for such a long time frame, then we need to make a little bit of predictions into the future. We need to think what is coming, what will happen in the next 100 years. If you're going back 100 years and you told somebody about mobile phones and internet, yeah, they would be laughing at you, and that you're having a printer at home standing in your office, and you're having a machine that you can talk to, and it's talking with everybody here now in Australia. Like, they wouldn't believe that. They couldn't imagine that. So what will happen in the next 100 years that impacts your building, or how your building will be performing? And there comes now in climate change, that is important. City development, yeah, is that building can we use that building at that location for 100 years, or do we need to move it? We have to move to a sustainable energy economy. In other words, we have to move to solar, wind, geothermal, water power. All that is happening in the next 100 years, and we have to expect that this happens. And then we have to think about the seasons when more energy is available. And then we're realizing cooling is not an issue. Cooling is only needed when the sun is shining. And when the sun is shining, energy is spot cheap. Like, it costs us 2 cents per kilowatt hour in the moment, and probably in the future this could even be halved again to 1 cent. We have to think about the storage, that in the storage process we're always losing a lot. We might get our efficiency from 30% maybe to a 40%, when we're lucky maybe to 50%, but physically it's not really possible with our understanding of physics today to get a more efficiency than 50%. And now, because of the economical implementation, only produce the energy in the summer and now use the energy in the winter, the cycle of energy use from summer to winter, that means we have only 1 time in the year that we can use it. And when we speak about investment and having only a cycle once a year, then storage from the seasonal storage starts to be really, really expensive compared to something like a little battery, like your power wall that you're having in your house that has every day a cycle. So you could have up to 350 cycles. So the economical implementation of short-term storage is far easier than long-term storage. And when we keep that in mind, then we know that heating will be far more expensive in 50 years than today. And we should think about that already in our design process, and making sure that our building is designed for the heating period, and making sure that the heating is as small as possible, and the cooling, we're not so much worried about it, because the cooling can be always done when the sun is shining and the energy is costing us nearly nothing. Germany has already a situation on really sunny days that the energy price, the electrical price, goes into the negative. So you're actually getting money to take the energy out of the grid. You're getting money by using energy. So we're having negative energy prices in Europe already because of overproduction in that sunny days. And this is what we have to keep in mind as well in our design. And that's what we went through a lot yesterday. At the end, the solution for passive houses is heat pumps for domestic hot water and for heating and cooling. The limitation of heat pumps is that thermal difference of 60 Kelvin that we have. So if the temperature drops below minus 20 degrees, then we're having that problem that the heat pump doesn't work any longer. And then probably burning stuff, having a liquid fuel that we can fuel that we can burn, or a gas that we can burn, is then probably the right solution for that location in a cold, really cold climate. So we have to keep that in mind. And then the limitation of the noise a little bit. But we're seeing already that there are new technologies coming on the market, because there's a bigger demand, and now scientists out there are working on it. We have this bimetal development with having two metals connected together, and they're now bending by temperature change, and by that they're absorbing and releasing heat. How that works, I have no clue, but it has been big in the news through a lot of science papers. So I think it's legit. I think there is something coming. So we have to stay on top of technology that is out there. And then in a passive house, the compact unit that is now doing the hot water system, that is doing the heating and cooling of the house, that is doing the ventilation of the house, and the storage of the hot water, all that in one unit, that seems to be the way to go. Right now, it's not economical here in Australia or in most places in the world yet. However, in the future, this will most likely be the common way of handling all our thermal needs in the building, except cooking and refrigeration. But maybe in the future, we find a way how to actually do that as well with the same system and connect them, and have now that losses of the fridge and of the cooking as well ducted back into our system. Who knows what is coming in the next 50 years. That's what we learned so far. Yeah, we learned how to calculate the thermal envelope. We learned how to design a heat recovery ventilation unit. We learned how to design our conditioning system and how to create hot water. And now we learn how to do that economical implementation. Some of that stuff is really big project economics. What you wouldn't, like if you explain what you're learning today to mom and dads in their process, they would probably not understand it. But on big projects, this is what we have to talk about resilient values, about return of investment, and all the bits and pieces. One thing, keeping in mind, what we're not talking about is today, and really seldom talk about, is the additional value added to the house. If you think about it, how much is like a certification, passive house certification probably costs you $5,000. On one hand, it's your insurance that a third party looked over it and the building is performing. But on the other hand, you have now a certificate from an independent party that says this building performs like XYZ. Is that worth in a resale value of $5,000? I would say in Australia, most likely it is. In nearly all the projects that somebody is willing to spend $5,000 more because it's a certified passive house, than saying, yeah, we designed it by the passive house principles, but it's not certified. Yeah, I think that certificate in a resale value has a value of $5,000, especially if you're selling it in not in the next 5 years, but 5 years onwards, when people understand passive house better in the region.